Hello, this is Team Wrexham's submission to the Spring 2016 Simio Student Competition. Today we're going to be talking about our project objectives, our modeling approach, our modeling verification and validation, our optimization strategy, and our recommendation. Project objectives are to identify strategies that reduce the amount of traveled work and determine the required changes to the system to handle an additional product type and ramp up. To assess this, we need some quantifiable objective functions, and the ones we've chosen are the amount of traveled work, so the total number, the actual total hours of traveled work, as well as modified man hours that accounts for overtime shifts. So the desired capabilities for a model are to model fixed cycle time servers while performing tasks and allowing for traveled work, while assessing the impact of changing mechanic mixture and the specific requirements for work cell 3. We want our mechanics to immediately stop working when they go off shift, as well as implement a learning curve for new mechanics. We also need some decision variables to model, so we want the mixture of trained and new mechanics, for non-traveled work, the mixture of original, current, and emergency work personnel for traveled work, as well as the number and shifts for each of these types of mechanics at each work cell. So we made modifications to the base server. We've subclassed it to make a server for fixed cycle time that also contains within it a MyServer to run tasks. And we're assuming that traveled work is not allowed to travel more than one single cell down the line. So what happens is an entity enters our work cell. We decide if it's traveled or not. We set a property to is traveled if this is true, and we start a process to wait for our previous test to finish. If it's false, we just move on and create a copy of our entity to send to the contained MyServer to run tasks. The original one just delays for set cycle time, then moves on to the next work cell. Our copied entity enters the MyServer to run tasks and completes the task list. Then once completed is destroyed, which triggers the event that resets our is-traveled state on our parent entity to false. We also want to model our mechanic selection mix, so we first check if our mechanics will be less than 12 at the station. If we see the right type of mechanics, then based on the work cell, job type, traveled versus not, and the user-defined mixed, we select mechanics based on not traveled or traveled properties. So we also need to make sure that our mechanics stop working when they're off shift. So the default logic in Simio is for actually the workers to finish a task, and which is usually acceptable because the server will follow that same shift schedule. However, because we want to control the shift schedule based on the mechanics, not the cell, we've added off-shift logic to release mechanics from their current jobs and interrupt the delays of the processes that model our task execution when a mechanic goes off shift. And then once they come back on shift and are seized by a task, that process delay is allowed to resume. The learning curve is calculated by assuming a steady-state production quantity and back calculating a process time multiplier for any new mechanics based on this equation, which is again based on the right model for learning. Then to calculate kind of an overall process time multiplier, we take the average of all the mechanics seized for this task, and then multiply the original baseline process time by this average. The model was built up in small steps to verify the logic along the way, along with a lot of color coding, graphs, traces, and animation to verify our logic. And so our entities will actually change colors and shapes based on different properties here. And for all of our workers seized by a task, they tell you which type of worker they are, as well as which task they're currently performing. Okay, we also want to make sure that we're selecting the right type of mechanics based on our user-defined preferences. So these are a plot of the mechanics seized by the work cell 1, and we see that when we prefer all trained mechanics, we get mostly trained mechanics unless we hit the maximum of 8. If we prefer 50-50 mix, we kind of get a balanced mix between the two. And if we prefer all new mechanics, we mostly get the new mechanics when we're selecting. So that's verified. Similarly, for our traveled work, we see that when we favor emergency, original, or current station mechanics, we get the desired seizures. And we also see when we have equal weighting, we kind of get a random seizure. And so this helps to verify our logic. So we see that in certain cases, choosing the correct number or the correct percentage of mechanics from our original work cell versus the new work cell really helps to control our traveled work hours. And this helps us to balance the desire to work on the current state of work with the need to finish our traveled work from before. We want to see the impact of the learning curve, and we see that if we prefer all experience, that will actually hinder our learning because those new mechanics aren't working as much, but we get more nominal results, and we kind of see the correct learning curve form here. Furthermore, if we change our steady-state production quantity assumption and make it larger, we get less learning, so it takes longer time to move down the learning curve. Okay, so to see our model in action here, we actually can see our workers moving around and completing tasks. So in work cell 5, we've actually finished all those tasks over there. We see our plots updating as workers move around and are seized by the different cells, and can see the current task that each mechanic is working on. So this gives you a very strong tool for model verification. To optimize the model, we leveraged OutQuest and the Pattern Frontier option, and we ran 3 scenarios based on the baseline new product mix with 1 and 2 lines. And the cycle time is updated such that it's the same for each. Because we assume that work travel more than one cell is a failed case, the provided baseline is actually infeasible. And so this is due to work cell 2 really building up traveled work and not maintaining feasibility. So while we don't match our baseline performance, this model is still valid because the tasks are verified as being processed correctly, and this discrepancy can be explained. However, to compare, we've created a modified baseline where we've added 2 Saturday shifts for work cell 2 over the baseline. Okay, so here we're presenting the results from our optimization experiment, and so we're presenting the 80th quantile of the results to help us reduce risk. So on the y-axis, we've plotted our traveled work and traveled work time against our modified man hours. And we really see that we can really reduce the amount of traveled work with minimal increases in cost compared to the baseline. And then so for further analysis, we're going to look at the points in the knee of the curve. So this first point here, we see that we've basically added weekend shifts, so Saturday and Sunday shifts, while controlling costs by reducing the number of trained mechanics we're using for each shift. And this is a very kind of similar strategy here, where we just added a few extra mechanics for this second one. Okay, so the optimized scenarios presented are reducing traveled work by adding shifts and then controlling costs by reducing the mechanics per shift, which makes sense because we can't always utilize the 8 trained mechanics, so it's really better to have more shifts with fewer personnel. But to really choose between these two, we need to really know how much cost do we actually save by reducing this traveled work. Now for the new product baseline, so we see kind of a different strategy here where we've kept most of our trained workers and then only added 1 set of weekday shifts, and that's actually worked out pretty well. And this is similar to our baseline strategies where we have maybe a fewer number of workers but working on the weekend shifts. Okay, for this new product mix, the additional production line really allows us to increase our cycle time while still producing the same number of aircraft. And we've identified 2 strategies using the large complement of mechanics for only 3 weekday shifts, and kind of similar to the first, the baseline scenarios, a smaller number of mechanics per shift but have overtime. And so again, we kind of need some more information about the trades between additional workers and traveled work costs, and also should we avoid planning weekend shifts, or should we try to ensure we hire new workers, new mechanics to prepare for future ramp-ups. One of the main limitations in the previously presented optimization results is that any mechanics added to the third shifts are subject to the learning curve, which really limits the effectiveness of this third shift. So more likely mechanics would be pulled from first and second shift to work on third shift. And so the way I modeled this was saying that you can have a maximum of 5 trained mechanics during each shift, and then we've optimized this with our new product mix and 2 production lines, and hopefully can see some considerable cost savings. And so what we see is we actually do get a lot of cost savings. So we're at about 96,000 man hours, and with reasonable traveled work count and costs. And what has actually been done here is we've eliminated the need for the weekend shift, so we don't get that time and a half, but still get a lot of benefit from our third shift. Additionally, we see that our trained non-traveled experience probability is only 0.5, so we're actually taking a mixture of the new and trained workers to find this optimum case. And so just to compare to the other 2 points presented previously, we have a little bit more traveled work for this new point, but have significant cost savings as opposed to the original one. So the simulation has supported our project goals by analyzing potential ways to reduce the amount of traveled work, and identified that we need a new line to support the ramp-up. The simplifications made to our process time multiplication drove our model to use weekend shifts, but then when we kind of assumed that we were going to move some of our trained workers to third shift, we could kind of overcome some of these challenges. The emergency mechanics really don't seem to provide a cost-effective benefit, really because they're not utilized very highly. A mixture of current and original work cell mechanics processing travel jobs could be helpful to speed traveled work, while not getting too far behind on the original cell, and well as training new mechanics with the already trained mechanics really help us move down the learning curve more quickly while not incurring huge process time increases during training. And so with that, thank you for listening and for your consideration.